So here we go again with a new revision video. Today we're going to look at total internal reflection, which is one that people tend to struggle with in the waves topic. First up, it is just a special case. Great start, select a pen. It is just a special case for refraction. So if you're unsure about how to apply refraction calculations or rules, or if you're not sure about Snell's law or whatever you want to call it, then probably click on this hopefully floating magical advert and go to that video first and get your eye in with refraction. If you're already completely happy with refraction, then we'll carry on. So total internal reflection, which I will lazily call TIR throughout the video, hopefully, occurs when you go from a high refractive index, not you, I suppose the light wave would be a better wave, or any wave. We might be looking at other waves, but generally light waves. When the light wave passes from a high refractive index, remember was n, to a low refractive index. Refractive index, crumbs. Ah, jeez. This is a wonderful start. A bit rusty. Apologies. Low refractive index. Now, for some reason, I've written n for one, refractive index for the other one, but that's fine. So TR occurs when the light wave passes from a high n to a low n of refractive index. Remembering, they're probably going to be things like glass to air. Okay, because glass is 1.5 refractive index, air is 1. Or maybe water, which is 1.3, or diamond, or whatever. But it's generally something going from a high, well, has to be from a high refractive index to a low refractive index. It would not work. You cannot get total internal reflection when you go from air to glass. And remember, it is total internal reflection, but it is a special case of refraction. Okay, so some people get confused there. So as I said, we generally deal with glass, which is our 1.5 refractive index, and our air, which is our 1 refractive index. So we're clearly going from a high refractive index to a low refractive index if the light wave is going sort of from here, to here. We never draw light waves like that, but that's just showing you the direction that it might go in. So we're going to start off with just a rectangular block with a light beam of light already in it. Obviously we've already drawn the normal there at 90 degrees of the surface. So for example, if light is going there, I've just realised that you can't see the word glass on all of these, but that's fine. It says glass and not alas or whatever. So we've got a beam of red light. Unfortunately, I've chosen not to put the arrows on, so I'm going to have to keep putting those on. And it's going at a fairly shallow angle, and it's this would be our angle of incidence. And if it was just going straight, then it would go straight through like this. So if that was not passing between two different refractive index media, then it would go in a straight line, but it doesn't go in a straight line, it curves like this. So we've got angle of incidence there, angle of refraction there, and some arrows for good measure. Okay, so what we see is when light goes from a low refractive index, when light goes from a high refractive index, such as glass, to a low refractive index, which is air, it bends away from the normal, and that is super important, and that is why you cannot get total internal reflection with moving from air to glass. So we're going from a high n to a low n. Here's another example. We've increased the angle I a little bit. Again, this is what it would look like if there was no change in refractive index. And notice now that we've increased I, and this angle here has also increased. Remember, we always measure the angle between the normal line and the ray itself, so that's why we're looking there. So we've got a bigger value for I, so the refractive index, it's bent more as it's come out. And if we keep increasing I, bigger and bigger and bigger and bigger, we eventually get to a point where, that's what it looks like going straight, but eventually we get to this point here, where at certain angle of incidence, the angle of refraction is 90 degrees. Okay, so again, R equals 90 degrees. Okay, so our ray of light, our beam of light, is passing along the boundary of the air and the glass. Okay, the boundary between the high and low refractive index. And we call this the critical case. Okay, so the critical case is the point at which the angle of refraction is 90 degrees. Okay, and we say that this occurs when the angle of incidence is equal to C, which is the critical angle. Okay, so the critical angle is just a very specific angle of incidence where we get an angle of refraction of 90 degrees. Okay, now something weird, magical, impressive, whatever you want to think, happens just past this angle. If we increase the angle of incidence even more, we get this occurring. So this is our total internal reflection. Okay, because our air glass boundary is now behaving like a mirror. So fortunately the letters are the same, but here, law of reflection, angle of incidence equals the angle of reflection. And it's called total internal reflection because it's total, so all of the light gets reflected. It's internal, it stays within the block, it's reflected, it follows the law of reflection, it bounces out at the same angle it comes in at. So that's what it would look like inside a rectangular block. Often we use a D-shaped block or a semicircular block, and the reason is because if you shine a ray straight through, then here you don't get any refraction as it enters the glass block, because as long as you keep going to the middle of the glass block, then your angle of incidence here and here and here is always 90, and it can't bend any closer to the normal, so it just carries on in a straight line. So it means we don't have to worry about these angles out here. So as I said, these are generally the three cases. This is the sometimes known as the subcritical case. So we haven't achieved total internal reflection. We're still going from a high N to a low N. So here in this subcritical case, our angle of refraction is shown there, angle of incidence. There is, sometimes see this, a faint, achieve a faint colour, do a different colour. So it doesn't change colour, but this is just to indicate that there is a sort of faint ray, which should probably be a solid line. So there is a faint reflection, probably poor penmanship. Again, obeying the law of reflection, but that's only faint, and you see most of the light going and being refracted out the back. So that's the subcritical case, where we say here that I is less than C. So the angle of incidence is less than the critical angle in this subcritical case. In our critical case, okay, remember, in the critical case, the angle of incidence is equal to the critical angle, and we know it's the critical case because the angle of refraction equals 90 degrees. And as I said, it's the boundary between refraction happening at the back of the block and total internal reflection happening. So critical case, angle of incidence equals C, and I guess this is the supercritical case. So it's gone past critical, but this is where TIR has occurred, because we now have an angle of incidence which is greater than the critical angle. Okay, and now we have total internal reflection. All of the light is reflected within the block. Okay, and again, there are essentially two criteria for TIR. TIR needs, well, it needs the ray or the light or the wave or the beam, whatever you want to call it, to go from high refractive index to low refractive index. That's the first one. And also the angle of incidence must be greater than the critical angle. So those are your two rules, and if it obeys both of those, you get total internal reflection. If you don't, you don't. It's that simple. So if the angle of incidence is less than the critical angle, then we just get bog standard refraction. Okay. So the other bit you're going to need to be able to do is to deal with an equation, and it's a recall equation. So whenever you see recall in the specification, then you need to, funnily enough, be able to remember it. And the equation is, hopefully you can remember this, n equals 1 over sine c. So just like the Snell's law refraction equation, we've got to deal with sine. But this one, we've only really got two unknowns, so, or two quantities that we could find out. So it's a pretty simple bit of trig and rearranging. So if, for example, our refractive index is 1.41, and we've got our block of glass, and our light travels in, and there's our normal. Okay, so here is air, and this is a special glass which has got a different refractive index, which has got a refractive index of 1.41. So how would you find C, and what value for C would you get? So have a go, try and work out C. What sort of value of C would you get? And hopefully you've got an answer, but hopefully you've also seen that this can't happen because we've disobeyed the first rule. We've gone from a low refractive index of 1 to a higher refractive index of 1.4, so we can't actually do that. It's a stupid question. It's a better question if it goes like this. I don't know why I keep drawing the subcritical case, because we really need the critical case because we're trying to find the critical angle. So there's C, there's the rays there, that's a C. So we said n equals 1.41, C equals question mark. So we know that n equals 1 over sine C. So we can rearrange that by bringing the sine C up and the n down. So we end up with sine C equals 1 over n. And then to get rid of the sine, we can use the inverse sine function. So sine minus 1 over n. Okay, so for our example, I'm just going to move to a completely different part of the screen. Okay, for our example, C would equal inverse sine of 1 over 1.41, and hopefully when you crunch it through, that gives you a critical angle of 45 degrees-ish. Just watch out, remember your calculator does need to be in degrees. If it's got an R or a G at the top of the calculator display, then you need to figure out how to get it into D, because those other two aren't helpful. So that is how you would deal with finding critical angle from the refractive index. The other case, a D-shaped block. Again, let's see our critical case. Let's say our critical angle is 30 degrees. So C equals 30 degrees. What does n equal? Well, this is the easier one because we don't actually have to rearrange it. We just got to plug the numbers in. So n equals 1 over sine 30. And sine 30 is a half. So we end up with n equals 2, which is somewhere between glass at 1.5 and diamond at 2.4. So yeah, there are the equations you're going to need. We've looked at the diagrams you're going to need. They might ask you, oh actually let's do these real quick. They might give you a right angled triangle, which I've drawn very poorly. So we've got to imagine that that's a right angle, which it clearly isn't. So let's get rid of that, and then right, that's a much better approximation of the right angle triangle. So one of the things you might be given is this, which is used in bike reflectors. So you could have a beam of light coming from a car, which is blue for some reason, I'm not sure why. And then if we drew the normal here, we would see that that was 45 degrees. So it gets reflected at 45 degrees, which is handy because we've then turned through an angle of 90 degrees. And then if we draw our normal on down here as well, well, funnily enough, that's also 45 degrees. And then our ray comes back here at, you guessed it, 45 degrees. So it goes in, down, and back the way it came. It's called a retro reflector, and it's great because it's just based on this idea of using a right angle triangle to turn the light using total internal reflection. So you could be asked to draw that, and it's not that tricky, really, is it? The trick is figuring out that that's a 45-degree angle of incidence, and this would only occur if the material you're using has a critical angle of less than 45 degrees. So for example, for glass, its critical angle is about its refractive index is about 1.5, its critical angle is about 42 degrees. And because the critical angle is 42 degrees and our angle of incidence is 45 degrees, then because our angle of incidence is greater than our critical angle, and we've got a high refractive index there and a low refractive index there, okay, then we can get total internal reflection. And as I said, the great thing is angles of 45 degrees, 2 of those gives you 90 degrees, 2 of those gives you 180 degrees, so back the way it came. The other example is the periscope. Now you can see this is sort of not quite a right angle triangle, but it's close enough. So again here the light comes in, again we're assuming that n is about 1.5 and the critical angle is 42 degrees. So if we draw on our normal line, then our ray gets reflected at 45 degrees, total internal reflection, and this is great because you can use it in a periscope. So you can imagine in a periscope you've got a mirror here and a mirror here, so you can do it with mirrors like that, although that would be a weird periscope where, yeah, I'm not sure what you'd be looking at, or the ray could go the other way. So you can turn, you can look over stuff with the periscope. So you could imagine a similar right angle triangle at the top. So remember, this is, again, is a right angle triangle. So yeah, there's some bits on total internal reflection. Other sorts of questions, well, they could ask about fibre optics, which use total internal reflection. Have a look through those. They could say, what happens if you use an N of 1.33, which is water. If we do that, we find that the critical angle is, it says, quickly punching into calculator. So there, the critical angle for water is 48.7. Okay, so this wouldn't work with water, because if you shone it in at 45 degrees, it would still come out the back. And also you'd have a triangle made of water, which, yeah, might also be a problem. Anyway, we'll stop there because I'm rambling. Hope that's helpful. Bye.